So I want to talk to you about the LeBron James problem. So the problem is stated that LeBron James can jump 0.9 meters into the air, and it asks you to find the force that LeBron James exerts on the surface of the basketball court in order to jump that high into the air. The challenge of this problem is twofold. First, you have to decide what information you need, and you need to go to the internet and basically find that information, or estimate it if you can't find it on the internet. So the first thing you're going to need is you're going to need the mass of LeBron James. So you can go to the internet and you can find that the mass of LeBron James is about 250 pounds, which you should convert to kilograms immediately. That is about 113.5 kilograms. Next, I'd like you to try and figure out how to visualize this problem. This problem is a little tricky to visualize because it really is a problem in two phases. And so what I'm going to do is try and break up that motion into its two phases. So I'm going to use LeBron James's head as a reference point. So at some point, he crouches down like this in order to jump. So this is going to be a starting point, right, in his crouched position. So at this point, LJ is crouching. And his initial velocity, V0, is equal to 0. So then, from the crouch position, LeBron James pushes down on the basketball court until he is vertical, and after that, he's going to leave the basketball court. So he's going to start from not moving, and then he is going to accelerate upwards, like so. And let's suppose that he leaves the basketball court at this point. So, okay, so his body is straight at this point. And then once he leaves the basketball court and flies into the air, what happens? He starts to slow down. So from this point onwards, we will draw longer, shorter, shorter, and finally stopped. And so this is the highest point, and this is 0.9 meters above the point at which he left the court. So during this phase of the motion, his acceleration is downwards at negative 9.8 meters per second squared because he's in free fall. And during this phase of the motion, his acceleration is upwards at an unknown value. We don't know what it is. It's important for us to find this acceleration in order to figure out what the force is that he exerts on the basketball court in order to jump. We also don't know what his velocity is over here, and it's going to be important to find. And second, we know what his velocity is over here at the highest point. It's the point at which he turns around and falls back down, so his velocity over here is 0. The first order of business is to find V1 by analyzing the second phase of LeBron James's motion. Okay, and we need V1 because we need to know how fast he was accelerating in the first phase of the motion. The fact that he jumped 0.9 meters into the air is enough information for us to find V1. So I'm basically going to apply a kinematics equation to the second phase of the motion. So I'm simply going to translate from the coordinate system for the second phase of the motion to the equation. The final velocity in this phase is 0. The initial velocity is v1, which is what we want to find. And the acceleration during this phase is negative 9.8 meters per second squared. and the displacement for this phase is 0.9 meters. And so V1 is equal to the square root of 2 times, which is equal to about 4.2 meters per second. So now we know that V1 is equal to 4.2 meters per second. And now we're going to analyze the first phase of LeBron James's motion. So in this phase, he starts from a 0 velocity and he finishes with a velocity of 4.2 meters per second. And so the question is to find his acceleration. So if you're starting to get familiar with the equations for kinematics, you realize there's not enough information. We either need to know the amount of distance he covered, or we need to know the time that it took for him to accelerate through this from 0 to 4.2 meters per second. So we're going to have to do some estimation. So the question is, how are we going to do that? So a lot of people want to try and estimate the time interval, but honestly, I don't have a good sense of how long it takes to jump, okay? It's hard to estimate the time interval. It's actually much easier to estimate the height interval. So I'm probably a good reference. I'm 6'2". I'm not as tall as LeBron James, but I'm close. He's probably in the upper 6 feet range. So we're simply going to try and use me as a reference point. So I'll start here. This is my crouch position, and here is my straight position. That's about the length of my forearm, which is 40 centimeters. And so I suggest, we'll compensate for the fact that LeBron James is a little taller than me, and so we'll say that LeBron James goes through 50 centimeters from crouched to standing, and that's a reasonably good estimate of the distance that he travels through in the first phase of his motion. So now I've estimated that the crouched to standing phase of LeBron James's motion is about 0.5 meters. And so we can calculate his acceleration using the same equation as before. So now again, we'll just plug numbers into the equation from the first phase of the motion. So the final velocity is 4.2 meters per second. His initial velocity is 0, and his displacement is 0.5 meters. And that gives us an acceleration of about 17 meters per second squared. So now that I have LeBron James's acceleration, I can use this acceleration to analyze the forces using Newton's second law. So Newton's second law says that the acceleration of LeBron James is equal to the sum of all the forces exerted on LeBron James divided by the mass of LeBron James. In order to implement Newton's second law, I need to draw a force diagram for the first phase of LeBron James's motion. So this is when he's still in contact with the floor and he's jumping upwards. So if I draw a force diagram for LeBron James, there are two forces being exerted on him. There's the perpendicular component of the surface on LeBron James, and there's the force exerted by the Earth on LeBron James. And you notice that I drew this arrow longer than this arrow for an important reason, because I know that at this point he has an upward acceleration. And in order for that upward acceleration to occur, the surface needs to exert more force on LeBron James than the Earth does. The other thing I need to do, of course, is to remember to put this in a coordinate system. So let's make up as a positive y, just like it is over here. Let's keep it consistent. And so now we can start plugging into the equation. The acceleration of LeBron James is positive because up is positive, and we found that it was 17 meters per second. So I put positive 17 meters per second squared equals And now there's two forces being exerted on LeBron James. I'm going to translate from the force diagram. There's a positive force exerted by the surface minus the force exerted by the Earth divided by the mass of LeBron James, which is 113.5 kilograms. The next thing I need to do is to remember that the force exerted by the Earth on LeBron James is going to be equal to the mass of LeBron James times 10 meters per second squared, or 9.8. I don't really care. Again, this is an approximation problem. It doesn't really matter. And that is equal to 1,135 newtons. Just multiplying his mass by 10. And so I can plug this into the equation. And that should give you about 3,000 newtons, which is about 600 pounds. So the last thing to realize, of course, is that the force that the surface exerts on LeBron James is the Newton's third law, equal and opposite force of the force that LeBron James exerts on the surface. And so we have actually found the answer to our problem. The force that LeBron James exerts on the surface is equal to 3,000 newtons.